The core of my research is using techniques from applied harmonic analysis to understand deep learning, particularly for data with geometric structure. And that's going to be relevant to this talk for two reasons. One is that I am not an expert on biology. When I work on problems that are related to biology or cancer, there are other people on the project who are much more knowledgeable about those areas than I am. And so advanced apologies if I am not able to answer some questions from the audience. The other thing is that I tend to think from an algorithmic or mathematical perspective first, and then once I've developed these tools, how can I apply them, which means that the biology in this talk is going to be kind of backloaded. So in order to avoid people falling asleep before lunch, I'm going to motivate with an example, which I'll then get to again halfway through the talk, which is we got a data set of melanoma patients that were analyzed via MIBI imaging. And what we wind up with is we wind up with protein counts for each of the patients, which we think of then of every patient as a collection of proteins. Each protein is a point in high-dimensional space. And then, so therefore, every person is a point cloud, which we are going to assume that they satisfy the manifold hypothesis, although that could get me in hot water after this morning. And the goal is to produce machine learning methods which can predict whether or not the patient is going to respond to treatment or not. Where for most of this talk, we're going to treat this as a binary classification method, although at the very end, we're going to teach this as a four-class classification, where the classes are improves, stays the same, gets worse, or dies.
So I'm sorry, what would two of this Xi's be for the same patient biologically?
Oh, each Xi is a different cell. And so you've measured how much, you've measured, I believe it's 29 proteins in each cell in single cell data. And so you're a collection of cells, and I'm a different collection of cells. Yep. Okay. So with that said, the outline is I'm going to first do a brief overview of deep learning for Euclidean data, and I'm going to talk about a mathematical model of deep learning called the scattering transform. Then I'm going to talk about how this can be adapted to geometric deep learning, talk about two different types of graph neural networks, spectral and spatial, and how the scattering transform can fit into this. And then I'm going to talk about how to design neural networks for data that's assumed to satisfy the manifold hypothesis, or possibly not. Consistency guarantees, which do require the manifold hypothesis. And then at the end, I'm going to talk about some generalized graphs, such as hypergraphs that go for beyond pairwise relations, and simplicial complexes, which impose additional structure, somewhat related to the TDA we've heard about throughout various of the talks. So I'm going to begin with a formal definition of supervised learning. There's an unknown function from some set X to some set Y. You have access to finitely many evaluations. That's called training data. You assume that this function can be well approximated by some function in a parameterized family, and you try to find the best parameters that fit the data. A motivational example is to predict whether or not a customer will default on their loan based on, say, their age, their income, and their payment history. And this is a kind of a classical example in machine learning, but what I want to highlight here is that there's no obvious relationship between these three dimensions of data, the three features, or between the people in the data set in a classical sense. So I'm going to think about this as unstructured data, which, as a preview, the biological data sets, we're assuming there is some sort of relationship between the features that you're measuring, which is the kind of compare-contrast. In any case, what artificial neural networks do is they iteratively transform the data via an alternating sequence of linear and nonlinear operations. And then after they've produced this new transformed representation, they apply essentially logistic regression to the transformed representation. And the hope is that if you have a sufficiently good transform, the job of the classifier will be easy. And if you're really lucky, it might even look like that. So the focus of this talk is going to be on how to design a hidden representation where hopefully that picture becomes a reality. So formally, the hidden representation is done in an iterative manner where each step, each layer is a linear map, a matrix multiplication of the input feature vector, and then a nonlinear activation function, which is applied entry by entry. The nonlinear activation is designed by the user, whereas the entries of this matrix are learnable parameters. Now, the first big success of deep learning for structured data comes in the form of images. And here what structure means is that the features you're getting are the pixel intensities, and some pixels are next to other pixels, and they're laid out in a rectangular grid. And so convolutional neural networks are a subfamily of deep neural networks that exploit this, this fact that there's a relationship between adjacent pixels, and you can slide things around because there's a nice regular grid. And right around when CNNs were really starting to become the state of the art, about 15 years ago now, the scattering transform was introduced as a mathematical model to try to understand why these CNNs are so useful for image data. What this is a pre-designed network of a convolutional network where the convolutional filters, the circulant matrices from the previous slide, are designed in advance and they're chosen to be wavelets. And what this does is this separates the network architecture from the need to solve a non-convex optimization problem and allows you to prove theorems about the construction and their stability and invariance properties. I'm going to focus more on adaptations to this for the graph setting. But what I will say is that if you are interested in learning more about the original scattering transform, there is an excellent talk on the IPAM YouTube channel from Stefan Millat, who explains it in much more detail than I'm going to. But for me, the primary insight from this work is that convolutions are the right family of linear operations for image tests because they have the right symmetries. And the right symmetries could either mean invariance or equivariance depending on context. So as an illustration, I'm going to think about two machine learning tasks. The first is, are the eyes open in each of these pictures? And what I claim is that if you take this picture and you translate it, you slide it around, you have not changed the answer to this question. So what you want is you want a single hidden representation of the entire image, which is invariant to translations. Alternatively, you could have, say, well, where are the eyes? Now here, you want a hidden representation of every pixel. And if you were to translate the image, you'd want to translate the hidden representations in the same manner. So you want something that commutes with translations or is equivariant to translations. I'd also like to thank my collaborator, Holly Steach, for being good at art because I am bad at art. So in addition to being an excellent immunologist, she's also much better than me at creating figures. So the filters in the scattering transform are chosen to be wavelets. What a wavelet is essentially come up with is you take a mean zero function that is called a mother wavelet, and you'd look at dilations of this at different scales, which are traditionally chosen to be dyadic integers, and then you convolve each image with each of these dilated wavelet filters. And wavelets are a reasonable thing to use in a mathematical model of CNNs for a variety of reasons, some related to modeling of the visual cortex with wavelet filters. Others are that they're widely used in image processing because they're known to sparsify naturally occurring images. So given the wavelet transform, the scattering transform is meant to be a wavelet-based model of a CNN. So in each layer, you have a linear map, which is going to be a convolution against a wavelet filter. And then you apply a nonlinear activation function, which in scattering networks is typically chosen to be the complex modulus or absolute value. Reasons for this, see Stefan's talk on the YouTube channel. The short answer is it induces a little bit of extra additional translation invariance due to complex modulations of phase space. But yeah, and another thing which is worth noting is that when the scattering transform is used, what you do is you take all of these coefficients, where it's a wavelet nonlinearity for however many orders you want, and you input all of these as new transformed features to whatever your favorite classifier is. Now, a nice thing about designing the wavelets is you don't have to learn the wavelets, and learning the parameters of your network is great when data is abundant, but it requires lots of data. So the scattering transform is actually also naturally well suited to low data environments. A nice illustration of this comes from some work by Naoki Saito, where the goal is to detect underwater objects, namely bombs, that are on the surface of the ocean floor. And unlike, say, images of cats, we don't have millions of images of unexploded bombs on the ocean's floor. And at a risk of being controversial, that's probably a good thing. And now, if the data looked like this on the left, those are relatively clean images, and you could probably train a network on some big image data set, ImageNet, or whatever your favorite big data set is, and apply transfer learning. The problem is that's after you found the bombs. When they're submerged, there's not really a good candidate for transfer learning, but you're still able, since it's a pre-designed network, you're still able to get good results without the need of like a good transfer candidate. So that was the quick Euclidean portion of my talk. Now I'm going to pivot towards geometric deep learning, which tries to take the success of CNNs and the insights to the importance of symmetry in the data set and extend this to graphs or manifolds or other measure spaces, preferably in a manner that preserves the intrinsic structure of the data. The most widely studied family of tasks is node-level task, where you got one big graph. You've got features associated to every vertex on the graph, and the goal is to make predictions about individual vertices. So in this context, if you were to relabel the graph, if you were to permute the ordering of the vertices, you're going to want to make sure that your hidden representation of all the vertices is going to be permuted in the same manner. So you would want equivariance with respect to the permutation group, which is kind of the graph-level analog of the where are the eyes task. Now, alternatively, there's graph-level tasks where you might have a data set, say, of many different molecular graphs, and you're trying to make predictions of, is this molecule related to non-small cell lung cancer or another disease? What are the chemical properties of these molecules? And so here you're going to want a hidden representation of the entire graph, which is going to be invariant to permutations of the vertices, and also to rotations or translations in physical space. So this can be thought of as the graph analog of are the eyes open? Additionally, there's adaptations of this to manifolds or to point clouds subsampled from manifolds. So I'm going to reintroduce this melanoma data set where you've got a patient as a point cloud where there are points in high-dimensional space. Each point is a cell. The dimensions are the protein counts. And we're assuming this data satisfies the manifold hypothesis. And then we approximate the manifold by building a graph from the data points, which acts as a discrete scaffold of the underlying unknown manifold. So in any case, with graph neural networks, there's, broadly speaking, two common families. One of which is probably the most common is what's called a message-passing neural network, where essentially this can be thought of as adding an extra step to a deep neural network to promote smoothness. And what I'm going to primarily focus on is spectral graph neural networks, which are based on generalizations of the Fourier transform to the graph setting. And I would also like to note that this is a false dichotomy and that there's overlap between these two families.
Yes. I'm just a little confused, right? Because when you were doing the classical case, you used wavelets, which are really different than the Fourier basis. Right, I mean, right, those are different orthogonal bases for L2, right, that you're looking at, right? So here, right here, you say you want to be using, right, basically the spectrum, Laplacian eigenfunctions.
Right.
So those aren't localized, usually.
Correct. In a couple of slides, we're going to introduce geometric wavelets, so maybe I can come back to that.
Oh, okay.
Okay, yeah. So there's two, so in any case, for either of these, what you're doing is you're given a graph, you're given a feature matrix where there's n vertices, and you've got f features for every vertex. And the extremely obvious thing here is that you can look at this matrix in two different ways, which is you can think about it as a row stacked on top of a row, stacked on top of a row, stacked on top of a row, or you can think of this as a column next to a column, next to a column, next to a column. And while that's an obvious statement, if you think about these two different ways, you're actually going to develop two different forms of intuition on how to define a neural network in the graph setting. So message-passing neural networks are based on each row is a set of features associated to a vertex assumption. And what you're doing is you're essentially taking a standard deep neural network. At each layer, you're acting on the features. You're multiplying on the right by a weight matrix, where now the matrix is on the right because it's a row vector. And then you're performing an additional operation in each layer, which smooths the transform features over the graph to make similar hidden representations across adjacent neighbors. So these two steps, you can think about the smoothing operator as an aggregation, and the linear transformation on the right as being combinations of the features. So these are sometimes referred to as aggregate combined networks. Now, the spectral neural networks are based on interpreting every column as a function defined on the vertex set. And the key objective here is going to be the graph Laplacian, where you take the adjacency matrix of the graph and the diagonal degree matrix, which just counts how many friends each node has, and you subtract them. What's worth noting is that on the case of a cycle graph, this matrix becomes up to a constant multiple, the discrete second derivative, and its eigenvectors are known in closed form, and they are classical Fourier modes. So we can think about these eigenvectors as being a generalized Fourier basis. And so what we do is reasoning with analog to traditional convolution, where convolving two functions is multiplication in the Fourier domain, is we take the Fourier transform of a vector x, which is thought of as a signal or a function on the vertices of the graph. And we take the inner product against each eigenvector of the graph Laplacian, which is our generalized Fourier mode, in order to define a graph Fourier transform. And then we define convolution of two functions on the graph to be the unique linear operation, the unique bilinear operation which multiplies their Fourier coefficients. So the convolution theorem traditionally in analysis was a theorem. Now this theorem has become a definition. So it either got a promotion or a demotion depending on how you feel about theorems and definitions.
I don't know anything about this field. So the thing that you get when you do this graph convolution, right? Mm-hmm. You get a new vector. Mm-hmm. Is that vector an eigenvector for some Laplacian of some graph, some other graph? I mean, I'm a little like. Can you map that back to graphs in some way? Maybe this question is totally nonsense.
So you're, just to make sure, also, like you're summing over projections. Sorry, I just want to make sure I understand. You're summing over projections onto the kth eigenvector of the Laplacian. Is that right?
Yeah, exactly.
Okay, and then projecting again, and that becomes the coefficient of the.
Yeah.
Of the eigenvector.
So the set of UKs, the set of the eigenvectors are an O and B. So then for any function x. Oh yeah, sorry, orthonormal. Does that mean something else in Cantor? Okay, yeah. Sorry, yeah. This is an orthonormal basis. Yes. So for any function defined on the vertices of the graph, where we're going to also identify this as a vector in Rn, where the ith entry is equal to the value of the function at the ith vertex. So since this is an orthonormal basis, we always have that x is going to be equal to the summation of a coefficient. And then you can expand this in this basis where the coefficients are given by taking an inner product. So then if I wanted to do a convolution, what I would do is I would also have y. So this is the Fourier coefficient of y, this is the Fourier coefficient of x, and this is the unique symbol that has the Fourier coefficients, which multiply together.
My question was, it's not that we're doing an operation that takes graphs, two graphs into a graph or something.
I mean,
you don't interpret it back.
No, it's function.
It's functions on the graph, on one specific graph.
Yes.
One given graph. I'm sorry.
Exactly.
I mean, it takes it into some k-dimensional space.
At least in finite graphs, then all
N-dimensional.
function spaces are the same, and it's awesome because you don't have to think about Sobolev norms or anything. But this inputs a function on the vertex set and produces a new filtered function on the vertex set. Yeah. Maybe like a classical analog would be like an audio signal where you could convolve with a filter to like amplify the low frequency things, which like if you were like turning up the bass on your car stereo or something like that. Another thing which is worth noting is that in the classical case, the eigenvalues correspond to frequencies of the sine waves. And without going too far into it, that analog does carry over to the graph setting as well, which you can see from looking at the associated quadratic form. In any case, now I'm going to get to the point where I define diffusion wavelets, which is I'm going to take a diffusion matrix P. And there's actually a couple of different versions of this diffusion matrix and different versions of the scattering transforms. Which one is probably the most computationally efficient is to think about a lazy random walk matrix, where you think about a lazy random walker on the vertices of the graph. At every step, they flip a coin. If the coin comes up heads, they do nothing. If the coin comes up tails, they move to an arbitrary neighbor. Notably, the rows of this, so the ijth entry of this matrix is going to be the probability you move from vertex I to vertex j. The rows of these matrix are the probability distributions that were, I believe, called mu-I in Tuka's talk yesterday, of the local transition probabilities of the vertices. And you can also approximately think about this in the spectral domain, where this is, roughly speaking, it's going to be a first-order Taylor approximation of the heat semigroup associated to the graph Laplacian, where the exponentiation is defined in the Fourier basis. And so then with so this operator is constructed as a decreasing function of the graph Laplacian, which means it can be interpreted from the graph Fourier transform. Now, to define the wavelets, what we're doing is we're going to take powers of this at two different scales, and we're going to subtract them. So perhaps the simplest way to think about this is that these wavelets might be measuring how are my two-step neighbors different from my immediate neighbors? How are my friends of friends different than my friends? How are my fourth-order friends different from my second-order friends?
How are you getting the different scales? I'm confused. Did you do this a different number of times or something? I don't.
So the wavelets it's the matrix P raised to a different power.
Oh, I see. Okay.
So yeah, it's essentially you take that matrix, multiply it by itself 4 times, but you'd also multiply it by itself twice. You get 2 different matrices and you subtract them. Except that's not computationally efficient, so you actually do something else. But if we're pretending that things have infinite computing speed, you multiply the matrix, a bunch of matrix multiplications and subtractions.
Oh, I see. I didn't read it in the right order. Okay.
Oh, yeah.
I didn't read the P. No, I understand.
I think I also said it in the wrong order, so that might be why you read it in the wrong order.
Okay, now I understand.
And then I get it. But yeah, so if you look at these wavelets, which can be thought of in the spatial domain of, it's going to take a signal of a function on the vertices of the graph and filter it by looking at comparisons across different scales. If you expand this in the spectral domain, you can think about these as bandpass filters, where each of these wavelets is going to be capturing the part of a signal associated to different frequency bands. And essentially, with these generalized wavelets, the definition of the scattering transform is going to be the same as before. It's going to be an alternating sequence of wavelet convolutions and nonlinear activations. Also, 2 warnings. Standard one that for every talk I give, this has nothing to do with scattering in the sense of physics. Special warning for this conference, we've heard a lot of talk about overloaded terms that mean different things in different contexts. I'm pretty sure this means something different than other dimensions of diffusion that we've talked about this week. Now, in the case of a manifold, rather than the graph Laplacian, you would use the Laplace-Beltrami operator, essentially the second derivative on the manifold. And then you would look at the heat semigroup at different time scales, which are going to be chosen to be dyadic integers, and you're going to perform the subtraction. If you like to think about things probabilistically, you can think about this matrix PT as being the transition probability for a Brownian motion moving around your manifold after t seconds. Or you could think about this as what will help you solve the heat equation for how heat would diffuse over a curved space. So yeah, I guess, does this answer your question from earlier of how do we use wavelets versus the Fourier? Okay.
I mean, you didn't explain why this is, why this is sort of more local than, the way, why things should be sparser in this thing than in the Laplace basis. But that'll probably come up later.
Yeah, you'll get approximate sparsity, and I guess sparsity is maybe a little bit less of a motivation. It's more of looking to capture changes. A lot of traditional graph neural networks are really based on this heuristic that people are similar to their neighbors. And that's what happens when you're doing that smoothing operation, is you're basically enforcing that as an inductive bias. Whereas, sure, that's all well and good, but where do things change across different geometric scales is kind of the motivation for detecting this.
Can you deal with the situation in which things change very differently in different parts of a graph or different parts of the manifold at different scales? Like, how does that? Is that not a? Does that question not make sense? I'm sort of thinking abstractly and not sure how to verbalize it.
So I think that that's already baked in because you're going to apply the wavelet transform to the full graph, but you're going to do this for all the different wavelet scales. And so some of the wavelets would possibly respond over here, and then others would possibly respond over there. And the places where the signal is nearly constant, then none of them are going to do very much. The other thing which is worth noting is that this is designed for a fairly generic manifold. It's not assumed to be a 2D surface in 3D space. It's not assumed to have codimension 1 with respect to the ambient dimension. We do assume that it is compact, which we've been told is okay, I believe. But we've also been told that manifolds don't really exist, so I would like to mention some work that was by Joyce Chu, where we were able to extend this to more general measure spaces where, without getting too far into it, essentially if you have a matrix that acts like a Laplacian and that matrix has eigenbases, then you can push through all of the theory. So we can hopefully relax to whatever the real thing that single cell data satisfies. Hopefully this works there too. At least it does on the computer. In any case, given whatever your favorite family of wavelets, the scattering transform is then defined as an alternating sequence of wavelet filter, nonlinear activation, wavelet filter, nonlinear activation. If you like, you can perform some sort of low-pass filtering or smoothing before passing it into a classifier. Or if you want graph-level tasks, you can do some sort of global aggregation where you sum over the vertices to get a single set of features for the entire graph. And essentially in a variety of theorems, what we can show is that these generalizations of the scattering transform have similar theoretical guarantees to the original scattering transform, namely that objects which are intrinsically the same, either isometric manifolds or isomorphic graphs, are going to be represented the same way. And perhaps equally importantly, if it's a small deformation where it's like, say, a diffeomorphism between two manifolds that is close to being an isometry, these properties will hold it approximately. So with that said, there's, again, this motivation of point clouds from an unknown manifold. And when we do geometric scattering on this, paired with a multi-layer perceptron as a back-end classifier, we're able to get 71% accuracy. We're also able to visualize this data set using these wavelets with some additional tricks and show that they're continuous with respect to the Earth mover's distance, or an Earth mover's distance. Earlier this week, I saw there was a poster presented by Alex about extending to this where rather than having functions from the vertices to the reals, you have vertices to some vector space, which we're going to assume lies in the tangent bundle of the underlying manifold, which we're going to pretend exists. And essentially, this theory can be adapted there based on adapting techniques from vector diffusion maps based on Singer and Wu, where you take a block matrix, which allows for translations in local reference frames based off of a local PCA. Motivation example would be a wind field reconstruction, where you've got the Earth is round. Again, I know this is being recorded, and I think I can still say that. And there's wind that is going to be blowing, and it's going to be lying in the tangent plane of the manifold. Or in a more complex but biologically meaningful example would be the neural trajectories, where we've got 24 different neural measurements of a monkey pulling a lever at different time points. So we get a trajectory in 24-dimensional space. We take the numerical derivative of this and think about this as a neuronal velocity. The goal here is the toy task of predicting, is the monkey doing this, or are they doing that? Or I think there's 7 different directions the monkey is allowed to pull the lever. We slightly beat the competition by a non-statistically significant amount, but there's 2 things worth noting. 1, we're faster, and 2, The leading competitor, Marble, is also based on modeling the data as lying in the tangent bundle of a compact Riemannian manifold. So perhaps all models are wrong, but some are useful. Going beyond scattering, the question is, can we integrate these wavelets into more general families of neural networks where you've got a whole bunch of different operations where you learn combinations of the wavelets and the input channels and use other tricks? And the answer is that that can improve performance. We'll see that a method based on this, where you're using some additional tricks in the scattering, gets 81%, which as an additional theorem, 81 is a bigger number than 71. The top performing method of this is also using techniques from information theory to help inform the design of wavelets, where rather than using dyadic powers 2, 4, 8, we use different scales that capture the most information. You can build the graph in a variety of ways, KNN, with the Gaussian kernel. I'm short on time, so I'm not going to go there. But essentially what we can show for all of these things is that a continuum limit exists as the number of data points goes to infinity. So if you have infinite data, this will do exactly what you think it was. And then if you have a lot of data, hopefully it does approximately what you do. We are able to get a convergence rate, which depends on how the graph is built. Quick takeaway, sparser graphs require more data. But if you don't have a lot of data, you can build a dense graph because it's not that big. So either way, you win. You can also extend this going beyond pairwise relations to think about hypergraphs, where you've got hyper edges that have every edge could have an arbitrary number of vertices. Simple example would be like co-authorship, where one paper might have 4 co-authors and another paper might have 3 or 5 or 20. You develop a generalized diffusion operator, and then most of the rest of the construction works the same way, where you look at different powers, you do subtractions, and you get a generalized wavelet basis. Motivational application for this was some spatial transcriptoma data from Alzheimer patients. And what we're able to show is that this gets a slight improvement in accuracy versus just modeling the data as an ordinary graph. We've also considered many different graph constructions, where what we do is we apply a reweighting, multiple different reweightings of the data before building the KNN graph or whatever graph construction you want to use. And what you can think of as each of these views as putting more weight on different features. It's not directly related to feature importance in a classical sense, but it's highlighting different features in different views. And then we're able to develop a scattering-based network that does this. In the case where we use those reweighted features to build simplicial complexes, we have a custom VR filtration that we're able to differentiate through, leading to an end-to-end differentiable network. And we see that both on that melanoma data set and also on a data set from patient-derived organoids from colorectal patients, adding more views does appear to improve the accuracy method, although at additional computational cost. Additionally, this is a possible step towards explainability, where you can look at which features are given the most weight in each of these views. And if a given feature keeps appearing as being important in like a network that works well, this could hopefully be useful for some hypothesis generation that this seems like maybe it's a relevant biomarker. So I'll wrap up here and saying that convolutional networks work well for images, in part because they have the right symmetries. And geometric deep learning tries to take this insight and extend it to geometric data. The scattering transform is a wavelet-based model of convolution networks that can also be extended to the geometric setting. And we can use these insights to develop high-performing networks with other operations that go beyond the classical handcrafted scattering transform. And there may also be advantages to taking multiple learned views of the data.